This is my third video in my module on finding the rate of change of a graph at a given point. And in this video, we're actually going to now use the definition of the slope of a graph that we kind of developed in the last video, which is the slope of a graph at a given point is really the same thing as what the secant line gets really close to as the distance between the 2 points approaches 0. So this formula right here, we are going to put it to use, okay? And it's just kind of an example of how you run through the mechanics of using it. So the graph that we're going to pick on here is just our parent function f of x equals x squared. Perhaps we want to find the slope of this graph, or the rate of change of this graph at -2 comma f of -2, which is really how we should be writing this here. We say f of -2 is our y value, but that happens to be a positive 4. Before we get into this, we could approximate the slope of this graph at this given point. We say we could draw on a tangent line, which I'm very much rubbish at doing here. We say, okay, let's go find the slope of the tangent line right here. And just by looking at this, we say approximately what is the slope equal to? I notice that it goes like up 3, back 1. So maybe -3 is my slope, or the way I've drawn it here, we say down 4, right 1. So maybe somewhere between like -3 or approximately -4. We know it's decreasing, but these are both an ish, okay? So we're getting a guess. What we want to do is find a precise answer. And so we can actually do this by using our formula right here for the slope of a graph, okay? So let's go ahead and start with a few basic things. We say, well, we're going to have to evaluate this difference quotient here. So my first question happens to be this: what is the x value at which we are finding the slope? Okay, what is the point? What is its x value? And so we say its x value in this case is -2. So we say x equals -2. So what we're going to do is we're going to say the slope overall of my graph is actually equal to this, the limit. A lot of rewriting when we do these, as h goes to 0 of this. So we'd say it'd be f of our x value, which would be -2, plus h, that minus f of our x value, which is -2, and this is all over h. Now, if we're going to evaluate this limit, one way we could do it is we can make a graph, we could make a table, or what we could do is we could actually work with it algebraically, so direct substitution possibly. And what I want everybody to notice is this: if we were to actually directly substitute this in, I'll actually do this on the right over here because we're not going to get anywhere with it, but if we were to put a 0 in everywhere we see an h, we'd say we get f of -2 plus 0 goes in for our h minus f of -2 essentially all over 0, which is the same thing as f of -2 minus itself. And anything take away itself is going to be this, is 0 over 0. So we get this what we call indeterminate form. And all it means is this: it's not that the limit doesn't exist per se, it just means that you can't just evaluate it by direct substitution. So here's my #1 primary recommendation when we do graphs like this, when we use this formula, is off to the side, let's go find these two values. Let's go find f of -2 plus h and also f of -2, because we'll come back in and we'll plug them into these spots right here and then reevaluate our limits. So given the fact that, I'll go up over here, we say our function to begin with is f of x equals x squared. The two things I need to find are f of -2 plus h and f of -2. And to go with simple things first, I'm just going to tell you, let's do f of -2, which means everywhere I see an x in this formula, we're going to put in a -2. So I end up with this, I get 4. You know what, we're going to stick this in our pockets because that is what is going to go in right now. And then the next thing we need to find is f of -2 plus h. Now, this is just algebra, so like I don't know why people freak out about it. In our formula, we'll take out the x wherever I see it, and instead we're going to plug in this -2 plus h, so -2 plus h. Which, by the way, is -2 plus h times itself. And so we can do binomial expansions. This is actually a lot quicker, but we say, well, foiling this, we get 4. Minus 2h, so minus 4h is total. And then positive h and positive h is h squared. So essentially we get this. We get h squared minus 4h plus 4. Okay, so here's what we have in our pockets here, and we had a 4 here. So now going back down and re-evaluating this limit, what we say is this. We couldn't do this with direct substitution, but now let's plug in what we know about this. We have f of -2 plus h, which we got to be excuse me, this value here. So we have this. We have h squared minus 4h, and that was plus a 4. All of that now, minus f of -2, which we got up here to be 4. So we're just going to go plug her in there. We say 4. And then this is all over h. So we still haven't evaluated this limit. As a matter of fact, if you evaluate the limit now, you're still going to get indeterminate form. So what we can do is we can manipulate this. And the first thing I want everybody to notice is that these 4's up top, they cancel out. So here's what we have left. We have the limit as h goes to 0. Still haven't evaluated this yet. Of h squared minus 4h's all over h. And using what we call the dividing out technique here, we could see that the top has a common factor of h. So we'd say this is the limit as h goes to 0 of factoring the top and the bottom. We have h minus 4, and this is all over h, and these h's cancel out, and now we're left with finally this expression, the limit as h goes to 0 of h minus 4, which if you've done limits, you're aware that this is entirely different than what you started with, but has the same behavior as the original, at least graph at that point. So we could say direct substitution now yields this. We have 0 going in for h minus 4, and this is equal to, I guess I don't need those parentheses, negative 4. So let's talk about what we just found here. This is the slope at x equals negative 2. We were able to use the definition of a secant line and take its limit as h goes to 0 to find the slope of my graph exactly at this point. So our graph is changing at a rate of negative 4 units per every 1x. And also this, that is very, very much commensurate with what we had guesstimated here. It had gone down 4, making a mess here. I'll go ahead and redo this again. It had gone down 4 and right 1. It's just that this definition will always get us precisely the right answer. So I want to do one more here, and actually I want to use a line, and a line for a very good reason. This one says, use the definition of the slope of a graph to find the slope of the graph of g of x equal to negative 3x plus 5 at any point. Any point, as a matter of fact. So we get this here. First of all, we say the definition of the slope of the graph in the first place is the limit as h goes to 0 of this quantity, all over h. We say f of x plus h minus f of x. And so we're going to use this to find the slope of the graph at any point. Okay, so now this time I'm going to say I don't know necessarily what x is. I don't really need to know what x is for us to do this. We'll just get an expression for an answer. So we'll say, okay, go find the slope of this graph. Well, the first things I'm going to need to know are what are these two quantities? And again, we could just do this off on the side. We say, let's go find f of, say, x. Well, the good news is f of x, we already have it, f of x. And this is a g of x in this case. So maybe I'll go back and do this again. We say g of x, which I need for this quantity right here, is negative 3x plus 5. We didn't plug in an x value this time. Throw this in your back pocket. We're going to need it. Now we need g of x plus h, which means wherever I see an x, we're going to take it out, and we are going to place this in. So we say x plus h. And so to go ahead and distribute this, simplify it a little bit, we get this. We get negative 3x minus 3h, and that was plus a 5. And now I have this in my back pocket. So now we're going to go ahead and do this limit. So we say the slope of our graph using what we have over here is this. M equals the limit as h goes to 0 of this. F of x plus h, which we already have to be this quantity, we have negative 3x minus 3h plus 5. Now this is all minus g of x. Sorry, I keep saying f of x. And then we have this as originally negative 3x plus 5. And this is all over h. So again, let's go ahead and observe the top. One thing is just the algebra of the matter. I notice that this has a negative in front of it. I'm going to go ahead and make this a positive and flip all the signs in here, so this would become a big fat negative sign, so negative. But we get this. We see that our 5's, they cancel out. Those 5's are gone. And I also notice that my positive 3x and my negative 3x cancel out, and I'm left with negative 3h on top. So we have the slope of this graph as the limit as h goes to 0 of this. Negative 3h's over h. And direct substitution, again, doesn't work here, but we can go ahead and divide out the h's. And I'm left with this, the limit as h goes to 0 of negative 3. And what we know from previous exploration of limits is this. We'd say, well, what is this graph approaching as h goes to 0? Well, there's no h to plug in, so direct substitution yields a -3, but the limit of any constant is always itself. That line is always at a height of -3. So what we just determined was this. We found that the slope of this graph, this is what we found, the slope of this graph is -3, where at any x value, we left x general, but why is this true? The reason why it's true is because if you were to graph this point, 1, 2, 3, 4, 5, it has a y-intercept of 5, it goes down 3, right 1, so it goes to this point, and we say at any x value, what is the slope of this graph? Well, last time I checked, a line always has the same slope, and this graph always has a slope of -3, no matter what point you're looking at. Okay, so what I want to do is I want to distinguish between the first example that we had done over here. We said, let's go find the slope of this graph at a given x value when x was 2, and we had to go find, f of -2 and f of -2 plus h, where we actually plugged in an x value for 2. And this one over here where we said, let's leave x general. Let's go ahead and say g of x and g of x plus h, where this x value was not named. And what we were able to find in the second one was actually an overall slope formula. It is always this at every x value, whereas in the first one, we found the slope of the graph at a given x value. So in the last two examples here, we say in the first example, we wish to find the slope of the graph at a specific point CF of C, where that C was like -2. But we use this definition right here where we had actually plugged in the C value into those X value spots. But we say in the second example, we wish to find the slope of the graph at any point f of x, and this is what we're driving towards. We say in such cases, we'll use the same difference quotient, but we'll leave x alone. I promise you things still simplify down. But I say, with the exception of what we just did, which was a linear function, except for with linear functions, what I can tell you is in the second instance here, when you leave x alone, it always produces what we call a function of x, which we say we can use that function to find the slope at any point on this graph, when we'll refer to this slope function, where we left x alone, as the derivative function. So in the next video, we're going to define what we mean by the derivative and show how it's nice to have that formula so you can find the slope of the graph at any point x. Cheers.